Hello students. So up until last class we saw the Riemann integrable functions and how they are connected with the Riemannian sum, and how Riemannian sum is connected with definite integral, and we also looked into some properties of Riemann integrable function. Today we will list few more properties of Riemann integrable functions, and then we go to fundamental theorem of integral calculus and what do we mean by antiderivatives and primitive. So as I was mentioning about the properties, so another property, property 5 of Riemann integrability is if f is a Riemann integrable function, if f is a Riemann integrable function, then mod of f is also a Riemann integrable function, and we have integral from is less or equal to integral from a to b mod of fx dx. So and so that means the mod of function f is also Riemann integrable, and it satisfies this inequality. The sixth property in this regard is it's a little bit how to say towards the direction of what we have already studied in limit and limit, continuity and differentiability of two functions. So we know that if f and g are both how to say continuous, then some of the continuous functions would also be continuous, or how to say if you are calculating the limit, then in that case if limit of f and limit of g exist, then the sum of their limits or difference of their limits or product of their limits also exist. So here in this case also we have the similar theorem. So if f and g are two Riemann integrable functions, Riemann integrable functions, then sum of these two functions is also Riemann integrable, the difference of these two functions would also be Riemann integrable, and the product of these two functions would also be Riemann integrable. For the quotient you need to have how to say the non-zero condition on the function g, that g has to be non-zero throughout that interval a to b, and then we can talk about its Riemann integrability. So it's pretty much along the same line of limit and continuity, how to say properties of sum of two functions or difference of two functions and things like that. And again, for the proof of this theorem, I would recommend you to look into the books which I recommended. Next, in Riemann integrable functions, we have something called let me go to a new page, the primitive. We sometimes also call it as antiderivative. So the definition is, if f is a differentiable function, such that f dash is equal to a given function f on the closed interval a comma b, then the capital function f is called the antiderivative or the primitive, whichever you prefer, primitive of the function f. And sometimes we write it, and this function, and the function capital F is also called the integral function of f, integral function of f. So what do we mean by this? So it means that we can write the function f, this small f, we can write this function let me use a different notation. So we can write this function small f as, let us say, a to x ft dt. So the capital Fx can be expressed as the integral of the function small f, and if you take the derivative on both sides, then in that case the left hand side will be f dash x, which is equals to the function ft, and that capital F, based on this definition, is called as the antiderivative or the integral function of this small function f. And if you have, but you see that in order to write this expression, we need to have some special conditions on this function small f and capital F. We cannot just simply write every function capital F as this integral form. So the very first criteria in this regard is every continuous function. So every continuous function f possesses a primitive. That means if f is a continuous function, then it can be written as this integral form. So the very first criteria we need to have for the function small f is that it needs to be continuous, and then you can be able to write the capital F as the integral form of this small f. Now we can put this in a small theorem. So the theorem goes like this. So the first theorem is if a function f is bounded and integrable on AB, then the function f defined as capital F x equals to integral from a to x ft dt is continuous on AB, and if f is continuous on the closed interval AB, then capital F is the primitive, or you can write capital F dash x equals to small f x. So if you have the bounded function f small f, then in that case this continuity criteria is pretty much clear, because in order to show the continuous function, you take fx at a certain point, you take fx minus fc, integral from a to x ft minus integral from a to c ft, and from there ft is bounded. So it will be pretty much obvious to show the continuity of the function f, capital F, on this closed interval a b. However, if your small function f is continuous, then in that case your capital F is actually the antiderivative or the primitive of this small fx. And from this theorem, in a way, or from this definition, in a way, the fundamental theorem of integral calculus is motivated. So from here we can state our very important theorem of Riemann integration, which is basically fundamental theorem of integral calculus. So fundamental theorem of integral calculus says that let us say I write it as theorem. So I can write it in terms of theorem. The theorem says that a function f is bounded and integrable on the closed interval a b, and there exists a function f such that f dash x equals to small fx on the closed interval a b, then we can be able to write integral from a to b fx dx as fb minus fa. So that means if we have a function small fx, which is basically bounded and Riemann integrable on the closed interval a to b, and if we have f dash x equals to fx, then in that case the integration of the function small f from a to b can be written as the difference of this fb minus fb and fa. So this is also in a way our Newtonian integral. So Newtonian integral is also about finding an antiderivative, or finding how to say a primitive of the function, so that you can be able to write it as a how to say integral of that function. So what I mean is, so if we have something like I equals to integral from 1 to 2 x to the power 5 dx, then this is basically my small fx, and I need to find a function capital F such that capital f dash x equals to small fx. So this is all about finding an antiderivative, and if we can be able to find a capital F dash x of this type, such that capital F dash x equals to small fx, then in that case the integral would be nothing but the difference of that capital F at the point 2 minus the value of that capital F at the point 1. So in this case it is very easy to find out this capital F dash x. So here our capital F dash x would be, so here our capital F dash x would be x to the power 6 by 6. So this is our capital F dash x, and if I take the derivative of that capital F dash x, then we will obtain x to the power 5, and this x to the power 5 is our small fx here. And you see this is our capital fx, and if this is our capital fx, and capital Fx, then it's basically 2 to the power 6 by 6 minus 1 to the power 6 by 6, and that will be the answer. So based on this fundamental theorem of integral calculus, we can see that how a function and its antiderivative are connected, and it's one of the important theorems in integral calculus, and it's also very interesting, and I hope you were able to understand this. I would also try to give you some examples. So first let me state the two last theorems of this Riemann integrable functions before we jump into any example. So the first theorem is the first theorem which I am talking about is first mean value theorem. So the first mean value theorem says that if f and g are, so it's more or less like the mean value theorem which we studied in differential calculus. So in the differential calculus also you have a a function, differentiable function on an open interval a b, which is continuous on the closed interval a b. Then in that case you can be able to find a point c in between the interval a to b, such that f dash c can be written as fb minus fa by b minus a. So here it's pretty much the same. So we say that f and g are two Riemann integrable functions on the closed interval a b, and g keeps the same sign over a to b, then there exists a mu lying between the bounds of f such that the product of the integral from a to b fx times gx dx is equals to mu times integral from a to b gx dx. So this is the first mean value theorem, which says that if you have two Riemann integrable functions f and g, and the function g keeps the same sign over the interval a to b, then you have a you have a value basically mu, which is lying in between the upper bound and the lower bound of the function f. So the function f is assumed to be bounded because it is Riemann integrable, and this point mu can be in between anywhere in of the lower bound and upper bound. Then the product of the integral from a to b is equals to mu times the integral from a to b gx dx, and this is basically our first mean value theorem. So here you can see that instead of calculating the product of the integral, we have replaced the function value of the function f with its value mu. So this mu is attained somewhere. So mu is attained at any point on this interval a to b. So it can be at I don't know, x equals to x2 or x3, any such point in the closed interval a b, and that value mu is basically multiplied with the integral of the function gx from the point a to b, and that is actually that will actually give us the value of the product of the integral on the left hand side. So this is in a way a mean value theorem. So we are taking any value of the function f between the upper bound and lower bound. The next theorem in this regard is the second mean value theorem, which states that so the second mean value theorem says that second mean value so the second mean value theorem says that if integral from a to b fx dx and integral from a to b gx dx both exist, and f is monotonic on the interval a to b, then there exists a C in the closed interval a to b such that integral from a to b fx times gx dx is equals to integral from as fa times integral from a to c gx dx plus fb times integral from c to b gx dx. So this is another interesting theorem. So we have both Riemann integrable function f and g, so that these two definite integral exist, and the function f is actually monotonic on this closed interval a b. Then in that case we have a point c lying between a to b. So all we need is the monotonicity of the function f. Then we can be able to find a function c in this closed interval a b such that the product of the integral here is equals to fa times integral from a to c gx dx plus fb times integral from c to b gx dx. So that means in order to evaluate the product of the integral, we don't need to evaluate the product. All we have to find the value of the function f at the end points, and then just evaluating the integral gx from a to c and c to b, we can be able to find the value of the of this definite integral on the left hand side. So this is another how to say important theorem in this regard. So to the syllabus which I gave you earlier, there we in the first lecture we were sort of planning to cover the partition, definition of Riemann integrable functions, and some properties, and then mean value theorems. And so far we have covered the theoretical part, and since it is a very extensive topic, I would recommend you to look into the books of Piskunov, S.K. Mappa, also Santi Narayan, to know these things in detail. I will also try to work out 2 or 3 examples, probably just to give you an idea that what do we how to say mean by these integrability conditions, and how to say 1 or 2 examples on the fundamental theorem of integral calculus. Also, most of my lectures I will, since I prefer to write it here and work out the examples or theorems here, but some of my lectures would also include a PowerPoint presentation, and I will try to make things clear in those PowerPoint presentations as well. So it will be a mixture of both this writing on the board as well as a PPT, and in the next lecture we will look into a few examples related to Riemann integrability and fundamental theorem of integral calculus, and today we'll stop our lecture here. So thank you.